Anyway, let's start today's class. So now it's April. We took 1 month for this course. Actually the weather is so beautiful recently, and then so we can observe cherry blossom. So I think so I can observe, I can find many empty slots here. So I understand it, but so I hope everyone works hard until the end of the semester, and then also stay tuned, even though it's April. Okay. 어쨌든 4월이 속도 많이 피고 좋은 때이긴 한데, 항상 뭐 저도 그렇지만은 학부 때 4월 정도 되면 계속 시험도 봐야 되고, 사실 제일 날씨 좋을 때 항상 시험 보잖아요. 그러니까 어쩔 수 없죠. 근데 뭐 저 같은 경우는 한 학기에 3번 정도 봤는데, 고대는 한 중간고사, 기말고사 이렇게 딱 나눠져 있어서 사실 그 벚꽃 필 때 시험 보고 이렇게 하긴 했거든요. Okay. So let's start today's class. In the previous class, we learned how to implement first table. So actually the Boolean equations using basic gate. So actually we can implement the Boolean equations using two-level logic. So we also learned that we can implement the Boolean equations using SOP form or POS form. Okay, so which means that using the literals, so we can implement the Boolean equations using AND gates and OR gates. Okay, so I saw some examples. Also, we learned how to translate the AND OR gate into NAND gate. So we can translate the OR AND gate into NOR gate. Okay. So also Morgan theorem. So it's a bubble pusting. So it's very important actually. The Boolean equations is not tricky. So which means that everyone knows algebra, normal algebra, right? But Boolean algebra is much simpler than normal algebra, which means it's easy. It's easier than normal algebra. So, so the Morgan theorem is a unique theorem in the Boolean algebra. So, which means that it's important. Okay, so we can apply the Morgan theorem. So actually, so we can optimize the Boolean equations using the Morgan theorem. Okay. Okay. Also, we learned about the illegal values x. Okay, x means the contention. So you need to understand that we are implementing hardware, which means that zero circuits. Then actually, the zero circuits are implemented using transistors. So which means that the transistor receives control signals or input signals like this one. Okay, this one. So actually, the input signals are given to the gate of the transistor. Then, using this gate signal, the drain and source can be connected or disconnected. So, which means actually the output is actually this is the NMOS transistor. So, one of node is connected. So one of node of NMOS transistor is connected to ground. So another node is connected to the output. So which means actually using the current flows from VDD to ground besides the output signals of zero circuit. So it is called that this circuit drives. So that's why this circuit is called a driver. So driver means that if a certain circuit generates output signals, the active output signals, and this circuit is called a driver. So I explained that this is not a correct circuit. Why? Because the same node is driven by two drivers. So, and then also I explained that 0, 0 is okay, or 1, 1. So if the output of this driver is 1, 0, 1, 0, so the output of this driver is 0, then it's okay because the two drivers are driving the same output. So output becomes 0. Also 1, 1 is okay because the output will become 1. But if the outputs are 0 or 1 or 1 or 0, then you cannot decide the value of this node. So actually, you already know that actually normally in the circuit, then we can also expect that 1, 0 or 0, 1 can be driven by these two drivers. So which means that we don't know. For these cases, we don't know the exact voltage levels or exact output value of this node. So this is called contention. So contention means that the same node is driven by two drivers, but two outputs of different circuits. So if our digital circuits generate contention, then this is an error. Okay, this is not a correct design. So this is an error. So if the incorrect circuits are generated by our design, then which means that our design includes a critical bug or critical error. So which means that we cannot use this system. Okay, it's a critical bug. So it's hardware. So which means that if we find a critical bug in software, then we can fix it. Okay, so we can fix our software, we can fix our program code. But if a bug or critical errors are found in hardware, it cannot be fixed. So it is because it's hardware. It's already actually the hardware is implemented using silicon. So which means that the silicon is a kind of sand or it's a similar material of sand or rock. It's actually stone. So which means that we cannot fix it. We cannot modify. It's very hard. Okay. So we have to avoid this situation, the contention. Okay. Also, we can define another signal value Z. So Z means that high impedance. So what does that mean? So actually we learn when you learn the electric circuits, then electric circuit is actually includes the voltage source, and then also the voltage source is connected to the resistance. Okay. Also, you can define some other components like the capacitors or some impedance component. So actually, so we can think about the resistance R. Then actually this can be also called the impedance. Okay. So what does high impedance mean? So high impedance means that actually the resistance is very high. Which means if the resistance of the circuit is very high, then current cannot flow through this circuit, right? So you know, in this electric circuit, the R is the infinite, then actually the circuit is, which means that this circuit is connected because the impedance is very high, so resistance is very high, so which means that the circuit is connected, right? Then current cannot flow through this circuit, right? So actually we can define this situation, okay? And then this situation, so we represent this situation using the high impedance. So Z means that high impedance. So which means it's the disconnected. The circuit is disconnected. So actually we learned about the transmission gate, right? Transmission gate looks like this. So we can combine MOS transistor and a PMOS transistor to implement transmission gate. So, and based on the enable signal, this circuit can be connected or disconnected, right? Using the PMOS transistor and MOS transistor, we can make this circuit connected or disconnected. So which means that actually this is the output. So actually this is the input of the transmission gate, and this is the output of transmission gate. Okay. So which means that we need to represent this output value. Okay. So in order to represent this output value, then we use Z. So Z means the high impedance. So which means that the circuit is not connected, it's disconnected. So this is the example of the circuit that requires the high Z signal. So sometimes it is called high Z because if we just use the Z, so the pronunciation is very short. So sometimes we use high Z. So it's called the high Z. It represents the high impedance. So this is the example circuit that requires high Z signal. So it is called a tri-state buffer. Okay. So why tri-state? So tri means three, okay, and state. So actually, this the circuit. I explained that this circuit have only two levels, 0 and 1. But this circuit has another output signal, it's high Z, okay, high impedance. So tri-state buffer has two inputs, like this is input A and this is the control input signal. So it's called E or enable. So based on this enable signal, the Y can be connected to A or Y can be disconnected from A. Okay, so Y is disconnected from A, and Y means the high Z because it's disconnected. Okay, so the tri-state buffer, if the enable signal E signal is 0, then Y is disconnected. So we need to use high Z to represent the output Y. Okay, and then if the enable signal is 1, then A is just connected to Y. So if the A is 0, then Y becomes 0. If A is 1, then Y becomes 1. Okay. So we can define another signal value, high Z, is the high impedance. Now actually we can implement this tri-state buffer like this. So as you can see, the enable bar is connected to the PMOS transistor here. So the enable is connected to this MOS transistor. If the enable signal is 0, then MOS transistor is disabled. So PMOS transistor is also disabled because this is the enable bar. Okay. So which means that this is disconnected. It's disconnected. So what does that mean? So output Y is disconnected from VDD or ground. So So which means wide disconnected from VDD or ground. So in order to represent this output, then we need to use the V. Okay. So we use tri-state buffer for implementing a bus. Okay. So what is a bus? So bus is a wire, and then actually this wire can be connected to many different components. So actually in a computer system, so we have many different I/O devices. So I/O devices means that input and output devices. So actually these input and output devices are connected to CPU via interconnection buses. Okay, so it's called a bus. So actually, when we implement a bus, then same wire can be shared by multiple devices. Then what's the matter? What is the problem? So we already learned that if a same wire, so or same node is driven by multiple drivers, so this is wrong. This is wrong. Okay, so it's incorrect implementation. So this is wrong, but we can implement this shared bus using tri-state buffer. So how? So we can connect the different components using tri-state buffer like this. Okay. So this is the driver part, and then also this is the receiver part. So as you can see, the driver is connected to this shared bus, yeah, tri-state buffer. Okay. Also, this device is what these components receive some signals from a shared bus. So, which means that we can enable only one of these devices using tri-state buffer. So, which means that if this processor is enabled, then you can set EN as 1. So actually, this line is activated. But at the same time, enable 2 is 0, enable 3 is 0, and then enable 4 is 0. So what does that mean? It is connected, disconnected, and disconnected. Okay. So which means this shared bus, so same node, is only driven by this component because the enable 1 is 1 and other enable signals are all 0. So disconnected, disconnected, and disconnected. The shared bus can be only driven by a processor, this component. Okay, so we can implement the shared bus like this. And then shared bus can be also shared by multiple components. And then using the tri-state buffer, then we can connect the multiple drivers. But we can implement this shared bus like this because we can use the tri-state buffer. But if multiple enable signals become 1, and it will work incorrectly, right? So we need to avoid that situation. So which means that for this bus, so if we implement a shared bus using tri-state buffer, then only one of control signal need to be 1. Okay. So actually we learned a bit, of the circuit can have 4 signals, right? The 0 and 1, that's what we learned, and X contention, and high Z. It's a high impedance. So actually, the next class will actually end up with. So we will also learn about the system value, it's a hardware description and VG, and so we can also find the signal X, Y, Z. Okay. So just remember that, so this is the circuit. So even though we're learning about the circuit, the system, and then we also learned that this system has can have only two values, but this is a circuit, the electric circuit. So we can also define the high contention, also high impedance. Okay, so X means the contention, right? And then Z means high impedance. Okay, so please read the textbook. And then let's move on. Karnaugh Map. Okay, let's learn about the Karnaugh Map. So what is the Karnaugh Map? So Karnaugh Maps, so it is also called K-maps. It's not Korean. It's a Karnaugh Maps. Actually, Karnaugh Map is a graphical method for optimizing Boolean equations. Okay, so this is the, so that I will show the example. I take the example. So this is the truth table of a certain Boolean equation, and then also we learned that using SOP form or POS form, we can implement log this Boolean equation using basic logic gates. But this this implementation is not optimized. So in order to optimize the Boolean equations, we can also use the axioms or theorems of Boolean algebra. Okay, but we can also use Karnaugh Maps. So Karnaugh Map is the graphical method that can be used for optimizing Boolean equations. Okay, so actually the Karnaugh Map exploit this theorem. What theorem? PA plus PA bar equal P. Right. So why? Is it because we can rewrite this equation like the PA plus A bar, and then we know that A plus A bar is 1. So P and 1 is equal P. Right. So what does that mean? Actually, if minterms include some same components and A and same component and A bar, then we can combine these two terms like some common terms. So because we can eliminate the A and A bar. And then actually Karnaugh Map exploits this property, this theorem, to optimize the Boolean equation. And how? So this is the example of Karnaugh Map. What can you observe? So actually this is the truth table, and then so this is the inputs. These are inputs A and B, and then C. Also, you can find that AB is here, input C is here. And then also you can find some numbers, some inputs like 0, 0, 0, 1, 1, 1, and 1, 0. So what does that mean? So this is the Karnaugh Map, and then in the Karnaugh Map, the AB represent the input values of inputs A and B. So because AB has two inputs, then we can have four different values for AB, right? So because of the two inputs, so AB can have 0, 0, 0, 1, Actually 1 0 1 1. Then also C, again C has only one input, so C can have 0 and 1. I will explain why we use the 1 1 here. So actually in this Karnaugh map, so this element represent the A is 0, B is 0, oh, why? A is 0, A is 0, B is 0, and C is 0. Okay, so which means it represents this row. This row. So what is the output of this row? 0, 0, 0. Each one, right? Then we can allocate the output Y using the main terms A bar, B bar, C bar for here. Right? How about the 0, 0, 1? 0, 0, 1. Output Y is the 1 here. So we can allocate the what output Y 1 here. And then 0, 1. So we can find 0, 1 here, right? Maybe. Oops. Okay, so we can find 0, 1 here. Sorry about that. Ah. Come on. Okay, so we can find AB01 in here. So it is 0, 1, and then also C is 0 and C is 1. So which means 0 is here and then 0 is here. And how about the 1, 0? And then also you need to note that 1, 0 is here. The next AB is 1, 0 usually in the truth table, but we can find 1, 0 here. Okay, so please be careful. So actually the order of AB is the 0, 0, 0, 1, and 1, 1, then 1, 0. So the 0, 0, 0, 1, 1, 0, 1, 1. Okay. Actually, this order is very important. Actually, so it is because we need to use this theorem. Okay, A plus A bar. So why? So if you see the AB here, so which means that it's the 0, 1 means that it's A bar B, and then 1, 1 means the A B. But if we use the 1, 0 here, right, then which means that it's A B bar. Okay, so which means actually if we allocate the 1, 0 here, then we cannot use this property, this theorem, because this means the A bar B, then this is the A B bar. So which means that we cannot allocate the some A and A bar in the neighbor rectangles, neighbor element. So please, so you need to remember that 1, 0 is here. So the order of the Karnaugh map is the 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so you need to remember this. It's very important. So 1, 0, AB 1, 0 is here, and then the C is 1, 0, and 1, and then the output of Y is the 0 and 0, and then 1, 1 is here, and then which means so 1, 1 is here, and we can allocate the output Y here. So actually the Karnaugh map, each element, like each element of Karnaugh map represent the mean terms. Okay, all right, mean term. So then let's see how to optimize the circuit, optimize the Boolean equations using Karnaugh map. So in this example, though, we can find 1 here. So what does that mean? So actually, this is the truth table that makes y ones, okay? And then using the min terms like a bar, b bar, c bar, and a bar, b bar, and c, then we can, right? We can make Boolean equations like this, right? Using min terms. Okay, that's what we learned. That's what we learned. And then actually, if we apply the Boolean theorem, then we can optimize this circuit, like because the a bar b bar is the common term, and then also we can use the distributivity theorem. So and then c bar plus c is eliminated. So this becomes the a bar b bar. But it's easy. But using the Karnaugh map also we applies the same optimization. So in the Karnaugh map, so we can find that the 1 are grouped in the, so 1 is here and then 1 is here, and then we can group these ones the Karnaugh map because these are in the neighbor elements. Okay, so 1 is here and then 1 is here, then we can group these ones. Okay, so and if the you can find that these columns of this Karnaugh map is all 1. So then we can actually represent this equation as only A and B, because for this C, then actually this group includes the all possible values of C. C is 0 and C is 1. So actually, if we can group this column like this, then we can represent this Boolean equation is only A and B. Okay, so A bar and B bar. So this is the example of the Karnaugh map. So which means that actually the truth table can be translated into Karnaugh maps like this, and then you can write output values in each element of the Karnaugh map. And then if we can find some neighbor element, if we can group neighbor elements and make it big, then we can group these elements. Then we can easily recognize the out input signals that can make the outputs. Okay. Okay. So this is the three. So let's see another example. So this is the 3 input Karnaugh maps. So as you can see, this is the truth table. Okay. So you know the AB is here, and then this is the values of AB is like 0, 0, 0, 1, 1, 1, 1, 0, and then this is the value of C. Then we firstly we need to assign output values in this Karnaugh map, right? Then what is this value? What is this value? It's a 0, right? Because it's a 0, 0, 0, and then this is also 0. How about this one? It's 1 and 1, and also you need to know that this is the 1, 0, and the 1, 0 is here. Okay, and how about these values? It's a 0, 0. Okay, and then it's 0, 1. Then how can we optimize? And then when we find some groups in the Karnaugh map, then we need to find the largest groups. So which means that actually we can find 1 is here, 1 is here, 1 is here. So which means that we can make Boolean equation using three methods. But we want optimize this Boolean equation using Karnaugh Maps. So which means we need to find the largest group. So in this example, the largest group is this one. We cannot group ones like this. Okay, it's not allowed. So actually, each group can include the number of elements like as the 1 power of 2, which means that 1, 2, 4, 8, not 3. 3 is not allowed. So each group needs to include number of the elements as the 1 element or 2 element or 4 elements like that. Okay. So in this example, the largest group is this one. Also, we can find the another large group. It's here. Okay. So and then so in this example, if we just focus on this group, okay, this group, then we can know that this group includes all possible values of C. So which means that this group represents the A, bar, and B, because A is 0 and bar B is 1. So which means the main term of this group is the A bar B. And then also, let's focus on this group. So actually this is easy, but let's focus on this group. So what can you observe? So in this group, actually the C is 1, right? And then this group includes all possible values of actually A, right? A is 0 and A is 1. So which means that the A can be removed. And then how about the B? B is always 1. So what does that mean? For this group, the optimized form is A is eliminated because A can be 0 and A can be 1. So it's the B. And also C is 1. It's the C. Okay. So actually this is the result. It's so hard to write using maps. So as I mentioned, we can group these elements and then these elements using Karnaugh Map, and then as I mentioned, using the this term, so which means that we can eliminate C because C has the all values for this group. So it means that A bar B, and then for this group, the A have the all values like 0 and 1. So A is eliminated. So this group becomes the B and C. So this is the optimized Boolean equation using Karnaugh Map. Okay. So if we just use the mean terms like the SOP form, then we need to use these mean terms, this mean term, and then this mean term. So which means that this Boolean equation will include three mean terms. But using Karnaugh Maps, we can optimize the Boolean equations like this. Okay, so this is some definitions we learned when we learned about the Boolean equation. Also, we can define another definition. It's a prime implicant. So in prime implicant instead is this is the implicant determined by largest circles of Karnaugh Map. Okay, it's called the prime implicant. So which means that these are prime implicants. Okay, these are so mean terms in the Boolean equations can be optimized. Then is optimized Boolean equations also include some implicants, and then these implicants are called prime implicants. Okay, optimized by Karnaugh Map. So this is the rule of using Karnaugh Maps. So this is the rule. Every one. So which means that the one means the output value one. So every one must be circled. So which means so when we optimize this Boolean equation in the Karnaugh Map, so we circle the is one, is one, is one. Okay. So groups includes the all ones, output one. So which means that you need to know that every one must be circled. Okay, at least once. So at least two. So which means, so if we see that this one, okay, this one. So you know this one can be shared by this group and another group. So which means that one can be shared by multiple groups, but we can remember that every one must be circled at least once. Okay, it should be included, and then each circle must span a power of two. It's also important. I explained that we cannot include the ones like this. Okay, it's not allowed. So actually, each circle must span a power of two. It means 1, 2, 4, 8, something like that, and then spheres in each direction. Each circle must be as large as possible. So what does that mean? So which means if this value is 1, then we can make large circle like this. Okay. So which it is okay, but it's not optimized. If we group the ones like this, then it is also possible, but it's not optimized. So which means that if this is 1, then we can use the largest circle like this. Okay. So each circle must be as large as possible. And then this is also important. Sometimes the circle may wrap around the edges. So what does that mean? Actually, so let us assume that this is 1, this is 1, this is 1, this is 1. Okay, this is all zeros. Then how can we group these ones? So you may think that, oh, this is the largest circle, and then this is the largest circle. So which means that we can in this Karnaugh Map, this Karnaugh Map, it has two groups, this group and this group, and that's okay. But it's not true. It is incorrect. So actually, Karnaugh Map is actually, even though we draw Karnaugh Map on the display surface, but actually the Karnaugh Map is connected like this. What does that mean? Actually, this part is connected to this line. Okay? The Karnaugh Map is connected like circle, the cylinder. Okay. So which means when if this is 1, this is 1, 1, 1, 1, then we can group ones like this. Okay, so it's very important. Sometimes so we can forget this rule. A circle may wrap around the edges. Okay, we may but you need to remember that actually this line and this line of the Karnaugh Map is connected. It looks like the cylinder. So which means that we can make large circle from here and here. Okay, this is very important actually. Sometimes we can forget this rule. Okay? So you need to remember that a circle may wrap around the edges. Okay, so this is another example. The 4-input Karnaugh Maps. Okay, so 4-input has the inputs A, B, and C, D, and A, B here, and C, D is here. Okay. So then, the AB is here. The AB0 is here. Okay, and then you can write the output value Y in each element of Karnaugh map. Then how? So 0, 0 is here, and then also the order of CD is 0, 0, 0, 1, 1, 1. Okay, 1, 0. So how can we allocate the output values? So it's the 1, 0, 1, 1, and 1 is here. Okay, so 0 is here, and this 1 is in the here. So 1, 0, 1, 1. Okay, we can allocate output values Y like this. Also, for this 0, 1, okay, so AB is 0, 1 here. So it's the 0, 1, 1, 1. And how? It's the 0, 0 is here, then 1. And then, this 1 is here, right? And then also 1 is here. How about the 1, 0? 1, 0 is actually here. Okay, you need to know that. So here, so it's a 1, 1, 1, 0. So 1, 1, 1, 0. Okay, so you need to note the order of is CD. So 1, 1, 1, 0. How about this one? So 0, 0, 0, 0, 0, 0, 0, 0. So we can fill each element of the Karnaugh maps like this. Then the next step is to group bonds. Okay. How? How can you find the largest circle in this Karnaugh map? What is the largest circle? So firstly, you can find the largest circle here. It's very easy, right? It's kind of elementary school puzzle, right? And then what is the largest circle? What are another largest circle? What is the number of elements in the another largest circle? So why did I ask this? So actually, this is also largest circle. So I remove this one. Okay. So you need to. So I mentioned that. So actually, the edges of Karnaugh maps are connected. Okay. So which means actually this edge is connected to this edge. Also another edge. This edge is also connected to this edge. So which means the largest circle is here. So sometimes we forget about that like this edge is connected to this edge, and then this edge is connected to this edge. But you need to remember that we can generate the largest rectangle like this. So because we need to connect it, so if we can find the 1, 1, 1 here, we can generate the largest circle like this. Okay. This is another largest circle. Then we cannot find any groups that can include the 4 elements. Okay. Then we need to find a group that includes the two elements. So actually, the ones are included by this group, the one largest group, and then another largest group here. Okay, so then we can have two ones here and here, right? These ones are not included in this group. Then how can we make groups for including these ones? What is the largest circle that can include these ones? So we can define a group like this, okay? So actually includes the two elements. Okay, for this one, then we need to define the largest group. The largest group is the possible largest group is one. Okay, right? So in this example, the ones are at least included each group. So which means that using the blue colored group, then these ones are included. And then using the yellow colored group, then so the yellow colored group includes this one and this one. But you know, so we need to group bonds using as large as circle. So it's the largest circle. So which means that this one should be included using also this one. Okay, then we need to generate the large group. So for this one and this one need to be included in a group using also this one. Okay. And then you know all ones are included in any groups, right? Then using like this, then inclusive like this, and then using the prime implicant, then we can optimize the Boolean equation. So actually, you can find the Boolean equation, optimized Boolean equation here. Okay. And then actually, each group includes represent this term and this term and this term and this term. So you know this is the 4-input Karnaugh map, and then if we use actually a certain group includes the 4-1, then we can represent this group using 2 inputs. Right? How? So let's focus on this group. So it's a green colored group. So in the green colored group, then we can find all possible Ds here. So 1, 0, right? And then also we can find that in this group, the B has the all possible values like here. So which means that in this group, B, we can eliminate B and we can eliminate B because B includes the B plus B bar, then B includes the B plus B bar. So it can be optimized, it can be removed. Then if we just see this group, then which means that A is 0 and then C is 1. So which means it represents the A bar because A is 0 and then C is 1. So which means that we can represent this group like the A bar C. Okay. So using the same way, then we can define another prime implicant of this Boolean equation like this, B bar and B bar. Okay, understand? So the purple colored group, it represents the B bar and B bar. Okay. Okay, this is the Karnaugh map. Also, when we optimize Boolean equation using Karnaugh map, now we can use. Then we can also consider the don't care. So what is don't care? What are don't cares? So actually we can use the symbol X to represent don't cares, right? But this X does not represent contention, okay? So when I explain about the symbol X, then I also explained that we need to understand the symbol X based on context. So sometimes X represent the don't care, okay? So which means that we can define two tables using don't cares. Okay, in the previous example, in the previous class, and then we can represent some inputs using don't cares, right? Then how can we apply Karnaugh maps using don't cares? So these are the rule what we learned. Okay, and then if the don't cares are included in the truth table, then we need to also consider the don't care. So which means we can circle don't care if it helps minimize the equation. So don't care means that the input can be 1 or 0, but it's don't care. So which means that it can be 1 or it can be 0. So which means if we consider don't care as 1, and it is helpful for optimizing Boolean equation, then we can include this. We can consider this don't care as 1. If not, then we can think that this don't care is 0. So which means you can think that don't care can be 1 or 0, and then if possible, so which means that if we consider don't care as 1, and if this consideration is helpful for optimizing Boolean equation, then we can think don't care as 1. And if not, then don't care can be 0. Okay, this is another rule, including don't cares. Okay, let's see the example. So this is the example. So in this example, so we can find, so this is the 4 input Karnaugh maps. So you can find that the outer Y is defined like this. But we can also find the Y includes the don't care. Don't care is here. Don't care, don't care, don't care, don't care, don't care. Then how can we fill each element of the Karnaugh map? With the same way, we can fill each element of the Karnaugh maps in the same way. So the AB is 0, 0, the AB is 0, 0. So this is the 1, 0. This 1 is here. 1, 1. Okay. How about this 1? 0, 1 is here. So 0. But this is don't care. So we can just mark this element as X because it's don't care. And then so 1 is here and 1 is here. So you can observe that I firstly mark 1 here and 1 here because you need to note down the order of CD. How about the 1, 0? So the 1, 0 is here. So which is 1, 1 and X, X. Okay. X. How about the 1, 1? The 1, 1, it's X, 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 X. Okay, so this is the first representation of the Karnaugh map. Then we need to generate the largest circle to optimize this Boolean equation. Then how? So, okay. Then what is the possible largest circle in this schema? So I explained that, so we can think x as 1, or we can think x as 0. Then in order to generate the largest circle, then we can think that these x are 1s, right? Then we can make the large circle like this. Okay? And then another case. What is the another large circle? Another large circle is this one. Okay? Oh, then you may think, oh, we can make the large circle like this, but is it required? No. Why? We don't make the large circle because actually this x is included, one is actually ones are also included. So we don't need to include this x. So we don't need to generate the another large circle like this. So actually this is not required. So we can think that this x is 0. Okay, this is 1. And then also another large circle, we can make another large circle. So which means that this 1 should be included. So we can include another large circle like this. Okay. Understand? So this is the result. So when we group 1 and don't cares, then we can think don't cares as 1 or 0. And we can think, we can decide the value of x for the how to optimize the best optimized between how for making the best optimized equations. Okay. So which means that we can make the largest circle including x, okay, if possible. So for this blue colored circle, then blue colored circle include these x's, because if we include these x's, these non-cares, then we can make largest circle. So which means that we can think this x is 1. So another example is this circle, this red colored circle. Also, if we think these x's are 1, then we can make this large circle, this red colored large circle. Also, but we need to remember, we need to note that this x is not included because we don't need to include this x. Okay. And then for this one, also the edges are connected. So which means that we can also make this circle. Okay. So this is the optimized Boolean equation. Okay. A, this is the A, the large circle, and then C, and this is the C, because the only the C is 1, and the A is 1 here. Then also another large circle, purple colored B bar and B bar. So actually the truth table includes non-care outputs. Actually the truth table includes the non-cares, then we can optimize Boolean equations more. It is because we can think x as 1 or we can think x as 0. Okay? But we can consider x for making the Boolean equation most optimized. Okay. So this is the end of the Karnaugh map. Okay. So please read the textbook. So just to remember that we using the Karnaugh map, so we can optimize the Boolean equations easily. Okay. So Karnaugh map is the graphical method for optimizing Boolean equations. But also you need to remember that the order of signals like 0, 0, 0, 1 COSE1011. Okay, this is very important. Also, you need to remember these rules, the payment rules. Okay, so if you follow these rules, then you can easily optimize the Boolean equation. Okay. Okay. Then, so I will briefly explain about the hardware description languages. So actually I posted the first design name, right? So I believe actually for the first design name, you can follow the instructions actually. Okay. So you need to install equals value. So this is the simulation tool for system value code, and then you can generate some very simple code like that. And the two, right? hello world of code using the system value. And you can simulate the system value using equals value. So equals value is the open source simulation tool. So actually, another goal of this course is to learn HDL, so hardware description languages. So actually, this course we will learn system value is widely used for HDL. Okay. Yeah. Okay. Actually, what's this photo? This photo is the type photo of the Intel Xeon CPU. Actually, I explained that Xeon CPU includes the billions of transistors, which means that actually a single CPU chip is very, very complex. So it includes the billions of transistors. Then how can we design this large chip, this complex system? So we learn we can apply some concepts like abstraction, so the hierarchical design, modular design, then so we can copy and paste some codes, some blocks. So, but each module is also complex. Then how can we design these complex digital circuits? Okay. So these are very complex design. Actually, when we design a chip, it's a VSI chip, then this slide shows the design flow of VSI design. Okay. So actually, the chip is implemented using CMOS transistors, okay, MOS transistors. So actually, the MOS transistors are product of semiconductor technology. It's actually silicon material. So which means that we need to implement this large chip using silicon. Okay. Then how can we? This is the common design flow of the data side design. So firstly, we need to specify the system, and then we need to define the architecture. Architecture is a kind of blueprint of the entire system, and then it includes the functional design and logic design. Actually, we are learning about the logic design. Okay, so using the basic gate or using some logics or some behavioral model of the this module, then we can design the small module like the AAU or some other elements. Then circuit design. So based on the logic design, circuit can be implemented. Okay? Which means that we can implement some circuits using the transistors, actually gate, like the AND or an exclusive or something like that. So we can, which means that we can implement digital circuit using basic gates. Okay, so from the logic design, the gates are generated, and each gate is connected each other. Then you can generate some digital circuit. But we need to combine simple modules, and then so which means that actually these circuits are integrated and then connected each other. And then this is called the physical design. And then physical design includes these steps. So actually these steps includes the partitioning, floor planning, placement, and the flexible synthesis. So this is actually the topics of the circuit design, so you don't need to understand. But you need to know that so actually not to implement a hardware or the chip, then it also includes the physical design, because it's a real hardware. It's a real hardware which is working in the real world. So which means that we need to define these steps. And then physical verification and sign-off. So which means that we need to verify the correct operation of this chip. So it's a physical design. Then sign-off means it's correct design, and then we just sign that it's the correct design. And then verification. So which means that the chip, the BSI, is manufactured the fab, like the TSMC or Samsung. Okay, so these are called fab. So it is because we can say that the chips are fabricated. That's why the TSMC or the Samsung are called fab. In the fab, then the silicon the wafer is fabricated, which means that it's actually then the most transistors are generated, and then with the packaging and the testing, and then we can make the chip. Actually, it's very complex. So, but in the digital design, then we can start from the stage. And then actually for this design, we use the hardware description languages. So this language is very similar to the programming language. So which means we have to generate, create software, and we need to write a code using high-level language. But in the digital design, it's the same. Not design circuit, then we can use hardware description language. So in the next class, we will learn about the basic of hardware description language. Okay. Thank you for attention. See you in the next class.